Hello everyone, I'm Ning Wang, a fourth-year student majoring in Electrical and Electronic Engineering of Technological University Dublin. Now I'm going to introduce my final year project to you. Okay, let's get started. The theme is visualizing voltage and current in an electrical circuit. Have you ever encountered any trouble identifying voltages and currents in the circuit? Since they are invisible to our eyes, it's difficult to understand them intuitively, especially for a circuit with so many nodes and branches. Is there a way to visualize them so that the node voltages and branch currents could be displayed graphically on a circuit diagram? That's what I presented today. My supervisor Ted Berg, who had provided a lot of help for me, and I really appreciate him. The presentation consists of 4 parts. The first one is the introduction to some key points of my project. Then I'll show you the implementation process, followed by a demo. The last is the conclusion of the key positive aspects and limitations. The objective of the project is to devise a new method of data visualization to augment a circuit diagram with a graphical representation of voltages and currents. Besides, the chosen method can be applied automatically to the output of a circuit simulation tool, so that the electrical state of the circuit could be understood at a glance by users. SVG, the abbreviation of Scalable Vector Graphics, is used as the image format of visualization. The method of my project is using the color to represent node voltages. The thickness of wires and the direction of arrows represent branch currents. As you can see in the figure, coloring different nodes with different colors indicates the voltage level. There is a legend on the right side explaining the colors, corresponding to the magnitude of voltages. The warmer color in the legend illustrates the positive value of voltage, and the colder color represents the negative value of voltage. A deeper color means a larger value. For the magnitude of currents, it's shown by the thickness of wires. Also, there's a solid arrow lying in the middle of each wire, which indicates the direction of currents. The size of it also corresponds to the magnitude of current. Furthermore, a tooltip function is used in this project. If a cursor is moving to any nodes or wires, there will be a value appearing near the cursor, so users can know the exact magnitude of node voltages or branch currents. For example, if I put a cursor on this node, 4.874 will occur, which is the current magnitude of the node voltage. Another interactive function, time controller, is included in the animation as well. The animation is replaying the output of simulation as a function of time. The transient simulation tab in our circuit simulation tool produces a discrete time signal for the node voltages and branch currents. That's a list of numerical values. Then the system translates that output into the animation that illustrates how the voltages and the currents vary over time. The user can click the play button to play the animation and then pause whenever they want. Also, the process bar can be dragged to anywhere in the timeline. In this way, users can easily see when and exactly what is happening in the circuit. Here are some circuit theories used in this project. It's about the visualization of node voltages and branch currents, so it's necessary to know what a node and branch is. Well, a node is a point where two or more circuit elements terminals are connected together, and the path between one node to another node is called a branch. So back to the last slide, in this circuit, there are actually two nodes. As for here, because it's grounded, I also put a yellow dot to show that reference point at 0 volt. And there are 3 branches. In this project, Kirchhoff's current law, KCL, is applied, which states that the current flowing into a node must be equal to the current flowing out of it. It can be reflected in this circuit. This wire is thicker than these two, and if you place a cursor on them, then you can see the current is equal to the sum of these two. Okay, let's see what resources required. This project includes simulation and software design. LT-SPICE was chosen as the circuit simulation tool. It was used to create a series of datasets containing the information to draw graphical images, and Python was used to parse the data information from the output files of LT-SPICE. JavaScript was used to generate the animation. Here is a set of things need to be downloaded. All of them can be downloaded from their official website freely. The most recent version of Python is Python 3, which was used in my project. LT-SPICE is a high-performance SPICE simulation software. Its file structure used to store the circuit and simulation output is much simpler to PSpice, another alternative as the simulation tool. Notepad++ was used as the text editor. After finish editing the code, you can run the Python file in the command window. And these two, svg.js and jQuery, are both lightweight JavaScript libraries. Okay, let's see the process flow. The first thing is to build a circuit and run simulation in LT-SPICE. Next, find the useful exported files containing the data of circuit and the simulation results. Then, pass data from the output files. And after learning how to draw some basic SVG elements, it's suggested to generate an example circuit diagram in SVG first, then generate the same circuit using JavaScript. The last part is to achieve the automation drawing, which is also the hardest part. In the first example circuit, a 5-volt voltage source is used, and it's in parallel with two resistors, 100 and 200 ohms. Dot trend 1 means that a transient time domain simulation of 1 second. After running simulation, we can see that from 0 to 1 second, all of the results are constant. 5 wires automatically generated after simulation. The AAC file contains the circuit description, including the coordinates of the circuit elements. The net file contains the netlist, describing which elements are connected with each other. The raw file contains the output of the simulation, but I just use AAC file and raw file in my project, which is helpful for my SVG drawing. The next step is to parse these files and achieve automation drawing. To achieve this, we need to know something first. Regular expression is a sequence of characters defining a search pattern. It's used while reading data from AAC file for string matching. JSON is a lightweight format in text for storing and transporting data. I use it to store the data from AAC file and raw file for SVG drawing in JavaScript. It's worth noting that data and function are separated with each other. Otherwise, automation can't be achieved. The function in JavaScript is to perform a particular task, such as drawing resistors in a circuit. I'll show you how to achieve it in the demo. Another two circuits are for testing. One is change the voltage source in AC. Another one is adding new components such as inductors, capacitors. For simplicity, I just call this the second circuit and this the third circuit. The first one is what we talked before. On the left side is original circuit built in LT-SPICE, and on the right is the SVG animation for visualizing voltages and currents. Now I'll show you how to get this animation. These two are the output files from LT-SPICE, ASC file and RAW file. We need to pass them first. In the raw file, the actual voltage and current data are at the end of the file in binary format, so some code needed to be written to unpack the data. This part is to pass those binary data in raw file, followed by data passing from ASC file. After reading those data, we need to store them in JSON format. To generate animation using JavaScript and save as the This file is what we created. Running the passing pattern file in the command window, the JSON format file was created, which we used in JavaScript. And it's the code for drawing. And that's what we got. Similarly, we can generate another two animations for the second and the third circuits. Overall, the main objectives of the project were met, except for the complete automation, and that's the key positive aspect. I've developed a new data visualization method successfully with the SVG animation presentation. The tooltip and time controller interactive functions are also achieved. It's the tooltip function, and it's a time controller. As you can see, this animation perfectly restored the circuit structure designed by the user himself or herself, which makes it a simple way to understand the circuit at a glance. But the limitation is that there are two things need to be typed manually: the coordinates of the nodes, the data assigned to the nodes and wires. This part is the coordinates of the nodes, and this part is for the data assignment. Because this data can't be obtained from LT-SPICE output files, therefore, if this could be solved, it would be definitely a huge improvement for future work. Thanks for watching.